Electrochemical potentials. Does anybody know what a chemical potential, DGDN, and we'll be more specific, where this is sort of number of moles, right, of some material, and this is the free energy. And this is good, this is useful, because it's going to tell us when things are in equilibrium. We'll talk a little bit about that today. It's useful for that. And we want to do something called the electrochemical potential to describe equilibria and thermodynamics of electrochemical cells. And it's related to the chemical potential. And the nomenclature here for chemical potential, electrochemical potential, you should be aware, is different in different books. What I call the electrochemical potential, some books actually call it chemical potential. Anyways, it gets a little confusing, but the key point here is electrochemical potential as defined in Barton Faulkner, and in the way I actually like to use it this way, I think it's very powerful, includes a sort of a chemical component and, as you might guess, an electrostatic component. So an energy associated with having charge and a potential. Because that's what we've talked a lot about, charge and electrostatic potentials, and now we have to incorporate that into our description of free energy and free energy changes into electrochemical. The electrochemical potential is what governs equilibria between two phases. So what do I mean by that? If two phases brought together, for example, silver and silver chloride, or a piece of platinum and a salt solution with some redox coupled in it, any two phases, and they're allowed to undergo chemical reactions with each other, exchange atoms, exchange charge, they will come to equilibrium, right? Given enough time. That's sort of one of the central tenets of chemistry. Right? The way we can rigorously articulate that is we say the electrochemical potential, call that mu bar. So mu is the chemical potential, we'll write that out in a second. In some phase alpha of some species I has to be equal at equilibrium to mu I in phase beta. So this is sort of the definition of equilibrium. And the way we can think about this is this electrochemical potential includes both the sort of intrinsic chemical energy associated with the given species, in this case species I, right? Could be I is just index, right? All different species in the system. So it includes that intrinsic chemical potential, energy, and then also if there is an electrostatic potential, if the species happens to change its capacity of charge, like sodium plus, right? Sodium plus is going to be attracted to a negative charges, so it will move down a hill in potential, down a slope in potential. So that we need to account for that in the free energy, right? So what we do is we say, okay, mu bar I of alpha equals mu alpha I plus the charge on I times Faraday's constant times phi, the electrostatic potential. This is going to be term 1, and this is going to be term 2. So this is looking pretty similar to some of the stuff we've seen before. Electrostatic potential times Faraday's constant. Faraday's constant is coulombs per mole, right? And this is just the charge, Z. This is the +1, +2, like sodium would be +1, right? Chloride would be -1. This term is basically the total charge in a mole of that species times the electrostatic potential. That just gives me an energy per mole. Okay, so this is basically going to be in kilojoules per mole typically, and both these have those units, both the intrinsic chemical part and the electrostatic part. Okay, so 1, as we wrote earlier, mu alpha I, this is called the chemical potential, and it's given by the partial derivative of free energy with respect to the molar quantity of species I at constant temperature, pressure. So what does that mean? That means if I add a little bit, like if I have like a boundary, say between silver and silver plus in the electrolyte, I can put a little bit of silver and make silver plus if I can put those electrons somewhere, right? And getting rid of silver, right, has some free energy exchange associated with it. And making silver plus has some free energy change associated with it. And so those free energy changes are represented by the chemical potential of silver and the chemical potential of silver plus. So it's just kind of like how much do you change the energy of the system by adding a little bit more of something or taking a little bit away of something per mole. So it's a molar quantity, right? This is kilojoules per mole. So with this, we can write pretty easily that delta G of some reaction is just going to be equal to the sum of, for all the species, NS is going to be the total number of species, the stoichiometric coefficient in front of the species times the chemical potential of that species. So what does that mean? So the stoichiometric coefficient, this is positive for products, like if you have, I don't know, 2 in front of a product, it would be plus 2. But it's negative for reactants. And so you can kind of see this. So this is basically just the sum of the chemical potentials of all species involved. So we could do it, we could do a simple example. A plus B goes to C. And we could write, okay, well, delta G of reaction, if I wanted to calculate that, equals C. Well, let's actually make 2C to make it more complicated. It'd be 2 mu C minus mu A minus mu B, right? Because when I take away a little bit of B, I make some C, but I make twice as much C, right? And so I can write that out. That's fine. So that's kind of how you relate it to these free energies we normally talk about. And now we want to think about the other part. Part 2, ZF phi. So we've talked about in phase alpha, I should say. This should be alpha here because the electrostatic potential might vary in the different phases. It actually might be a function of position in your system, right? If current is flowing, right, there's going to be a gradient in electrostatic potential, and that will affect the energy of the species at different points in your system. So if I have, for example, right, current flowing through a resistor, phi is going to drop through that resistor, right? If there's current flowing, this is IR, right? V equals IR. Not that complicated. And that's causing, in this case, positive charges to go that way, right? So the same thing in our electrochemical cell. Remember, we can think about the electrolyte sort of as an ionic resistor. And if you're flowing current, you need to have a little bit of change in potential with position in your electrolyte to get the current to flow. So let's think of this a little bit, brief review, briefly. If I think about phi, the electrostatic potential, the definition of phi, and now I'm going to write it in a little more general way. Function of x, y, and z. I can write it as in angular coordinates and radial coordinates and spherical coordinates, right? So it's a function of space, generally, right? And the definition is the negative of the line integral going from some place really way far away from where I'm interested in, infinitely far away, right, to that position, x, y, z. So it's a three-dimensional integral along the path you take to get there. So if you think about it, if I have some charges, or if I have some electric field distribution, if I go infinitely far away, the electric field is no longer going to be acting on me if I'm a charged particle, right? And I'm just going to walk closer and closer and measure to integrate up all the sort of force that I feel, right? Force normalized to my charge is actually the field, right? I'm going to integrate all that up to get essentially the work normalized by my charge, which is that's the definition of potential. An example, I have a charged sphere of metal, and I put some charge on there. Okay. I have an electric field, right? It's going away from that charged sphere. And if I go infinitely far away, I can have a positive test charge, and I can bring that test charge closer and just calculate how much energy it takes to move a chest charge of unit fundamental charge to any point around this sphere, and that tells me the electrostatic potential. Just charge moving towards the sphere. So if this is a conducting sphere, what does the electrostatic potential profile look like inside of it? So the charge has to sit at the edge of the metal. That's called Gauss's law. Well, I guess another way to say this is, instead of putting all the charge at the surface of the metal, I could also uniformly distribute the charge everywhere. So why would uniformly distributing the charge everywhere be higher in energy than putting all the charge at the edge? So imagine I had a metal sphere, okay, and I put two charges here and here. What's going to happen? Can charges move in a metal? So what, are those charges going to attract each other or repel each other? So what's that going to cause them to do? Move to the edge. And so that's a key feature of a conductor, ionic conductor, electronic conductor, so an electrolyte or a metal. You cannot support at equilibrium in the absence of current flow, in the absence of movement of charge. You cannot support an electric field inside of a material with a high concentration of mobile charge carriers, because if there was an electric field, the mobile charge carriers would just move. And that's kind of the basis for Gauss's law. You can, simply, if they have mobile charges and there was a field, they'd move. So you can't have a field in a metal. So we'll say if E exists in metal, charges would move to cancel it. So if E is electrostatic potential, E is electrostatic potential in volts, the unit for a volt is a joule per coulomb. Then as we wrote, Zi is charge number. It's a unitless number times F is coulombs per mole. So it's the charge per mole. This is Faraday's constant, right? Times electrostatic potential in joules per coulomb. And if you cancel this all out, you get joules per mole. Right? So that's an energy. And this is electrostatic work done to move 1 mole of species from x equals infinity to x alpha, of phase alpha. If I had an electrolyte and it had some electrostatic potential in that electrolyte, I could calculate the work needed to move those ions from infinitely far away into that electrolyte. So what happens if we take our conducting sphere? So let's take our conducting sphere with the charge on it, and we put it in a droplet of electrolyte, metal electrolyte. So remember at the beginning, there was a field coming off of this, right? Is the electrolyte a conductor or an insulator? Ionic conductor. You are right here. A Melli minus. Yes. You are going to move right here. What are you going to do? You're going to run away. You get as far away as you can, right? You're going to do that until you have made a double layer here and a double layer here, in fact, right? Now, how are the number of charges here and here related? Charges here, charges here, charges here. We'll call one like Q metal, Q electrolyte minus, and Q electrolyte plus. How are those three things related in magnitude? They're all equal, right? Because obviously this electrolyte phase is neutral overall. So if I put negative charge here, I better have positive charge on this outside this same magnitude. And the negative charge is going to completely screen this positive charge, so it needs to be the same magnitude. These are sitting directly next to each other, sort of in the Helmholtz layer. And say I put vacuum over here. Write the electrostatic potential distribution. So draw it on your notes. And let's make this a radial distance. And let's make this Rm, the radius of the metal. and RS, the radius of the sphere. And then this is going to be vacuum out here. This is going to be electrolyte. And this is going to be metal. Well, okay, so you think about it. So these charges all cancel these charges, right? But you still got some charge, excess charge on the outside. In fact, the excess charge is the same charge that was on the metal to start with. And in fact, if you remember from freshman physics, for a spherical charge distribution, the field from that charge distribution is identical to if that charge was all concentrated at a point at its center. So we could use Coulomb's law. Field's going to be 1 over r squared, goes 1 over r squared, the potential goes 1 over r. Calculate that, so you're going to fill 1 over r potential, right, approaching this charged sphere. And so let's do that. So let's start, well, what are you going to feel like way far away? Like you go to, you know,
like almost nothing.
Nothing, right? So it's got to start from nothing out here, okay? And then it's kind of got to go up as 1 over r, right? Kind of proportional to 1 over r. And then you hit this boundary, and there's all these positive charges, and you just step by them. Now what do you feel? You're in the electrolyte. As soon as you cross this boundary, you guys don't feel force anymore. And it has to do with because if you actually like added up all the interactions, they all cancel each other out. So that is why. So what should I write for there's no field? What should be the electrostatic potential here in this region? It should be a constant, right? So now, Will, you're back walking. It's really easy, you know, no force against you, no force pushing you. It's, you know, no wind at your back, no headwind. And you get here, and there's this big wall of negative charge and then a big wall of positive charge. And it's just, they're real close together, right? Because this is actually a continuum model, so they're infinitesimally close together. And you just go, was that easy or hard for you? Did you have to walk uphill, or was it kind of jumping downhill? So there's, at this interface, remember, there's a very strong field.
I imagine it'd be like hitting a brick wall.
It's like hitting a brick wall. You have to just like jump or do something to get up over that wall, right? Okay. So you get over the wall, and then what happens? Now you're in the metal. Are you happy here? Are you gonna be pushed anywhere? What's gonna happen? You're a test charge. You're an imaginary charge. You know, what are you gonna feel? Is somebody pushing you towards the center?
There should be no
force.
No charge.
No. So okay. So the potential should be what?
Constant.
This is the electrical double air that we've talked about before. A plate is a little bit different geometry. So you have, say you have a wall of positive charge here. And so the field coming off this is constant. Okay, so there's a constant field. And the reason it's a constant field, the reason it doesn't decay as you move farther away from that, it goes on forever. But you have to remember, this plate goes on forever too. So like every time I take a step back, like I'm kind of having more of what, like the same angle, you know, a solid angle, like has more charge in it. So I take another step back, and all of a sudden I'm seeing more charge and more charge. So every time I take a step back and the field gets weaker from the charge right in front of me, there's more charge acting on me, and they cancel each other out. So that's why an infinite sheet has a infinitely long field. And so if the field is constant, what does the electrostatic profile look like approaching a charged sheet? It has a constant slope, which means it is a line. So no matter how far Melly tries to get away, if she sees an infinite wall of positive charge and she's negative, okay, so now we see this, that mu bar alpha I equals mu alpha I plus zi f b alpha is just the energy. This is the chemical potential energy accounting for internal chemical energy and effect of field. Okay, so we'll do the properties of the electrochemical potential next. So properties of electrochemical potential, key. 1 mu bar equals mu in phase alpha for species I. When is this going to be true? This is for uncharged species. More generally, we can write mu alpha I equals mu naught alpha I plus RT ln the activity of species I, phase alpha, standard state, like delta G naught, right? Standard state. And this is an activity term, where A, I guess, is the activity of species I, RT ln AI, and this accounts for non-standard state concentrations or non-standard state activities, right? So something that's very dilute, right? If I have something concentrated, good example of how to use chemical potentials is if I have something concentrated, say I have 1 molar HCl over here, and I have a separator, and I have 0.1 molar HCl over here, and I pull that separator out, what happens? I mean, you know what's going to happen. They're going to mix and they're going to equalize, right? And that's going to happen because the HCl wants to go this way via diffusion down the concentration gradient, right? Which one do you think has the higher chemical potential? What do we know about things? Do things like to move to higher chemical potential or lower chemical potential? Lower, just like balls roll downhill. They go to lower gravitational potential, right? Reactions go to lower chemical potential, chemical processes. This has a higher chemical potential than this. That's because this has a higher activity than this. So this is actually a way to predict how this will come to equilibrium. Because we know in the end, the chemical potential has to be the same everywhere. Third rule, for a pure phase at unit activity, what does unit activity mean? 1 activity equals 1. We can write mu alpha I equals mu naught alpha. So basically, for a pure phase, I don't have the bar in my notes, and I think that's right because a pure phase, you can't have a pure phase that's not electrically neutral. I couldn't imagine like a macroscopic quantity of silver ions all sitting next to it. But we can also erase the bar. That's also true. So that's basically the definition of standard state. For electrons, we can define mu bar E alpha, electrochemical potential of electrons in a phase. This, by the way, is the Fermi level. For those of you who are thinking about solid state materials, it's the same thing, electrochemical potential of the electrons, Fermi level. So it's the reactivity of those electrons to do something, right? We can make that equal to mu naught E alpha minus F phi alpha. And so basically there's 2 components. For example, if I have a metal that has some work function, right? That metal work function dictates the intrinsic energy of the electrons in that metal, right? Because that's sort of how much energy it takes to get an electron out of the metal, right? So it's kind of telling me how reactive are those electrons. Sodium, right? Higher energy electrons, gold, lower energy electrons. But then I can also apply a field, and I can change the energy of the electrons with the potential from that field, right? And notice I disregarded activity effects. I disregarded changes to the concentration of electrons, because activity effects are usually negligible for electrons. And then 5, for equilibrium of I, species I, between alpha and beta, mu bar alpha I equals what? Mu bar beta I. So any species, right? These are not in equilibrium if I have a separator there, right? The concentrations are different. If I remove the separator and let it come to equilibrium, the concentrations, will they be different? No, because of this. But we have to have the bars there are useful in electrochemistry because we can have double layers that change the electrostatic potential on one side of the double layer versus the other side. We can have membranes and cells that have a potential across them. And so we need to account for that in our definition of equilibrium. Okay, so now let's consider some examples of electrochemical equilibrium. Gold and sodium in contact. What's going to happen if I put a piece of gold and a piece of sodium together? Sodium is probably going to donate electrons to gold, right? Will all the electrons flow to gold? About the electrochemical potential of the electrons if they're in equilibrium. What's this equal to? That's the definition of equilibrium. Okay, so we can do that. We can expand this. Mu AU of the electron minus F P AU equals mu of the electron sodium minus F P sodium. Notice here I'm subtracting Fp. That's because the charge on the electron is what? -1. So before it was plus ZFp. Z is -1, so it's minus Fe, right? And so I can solve this for negative F Phi AU minus Phi sodium equals mu E sodium minus mu E gold. The difference in the electrostatic potential that developed is going to be the difference in the work functions, basically. So if one's 3 volts and there's 5 volts, you're going to have a 2 volt electrostatic potential drop, equilibrated, right? So what it's going to look like, it's going to look like this. You're going to have gold and sodium. And which way was the electrons going to flow when I equilibrate them? Across this interface. So there's going to be some negative charge here. What's that going to leave behind? Positive charge. Why didn't I put the charge everywhere in the sodium and the gold? Well, first of all, they're metals, right? So it has to be the surface. And then, they're double layer, right? So they have to be electrostatic potential difference caused by charge transfer is due to a chemical potential difference of the two metals. So, if I wanted to draw like Fermi levels, like gold, EF gold, and write EF sodium. You touch them, electrons are going to flow downhill, right? Do another example. Say I have a cell, and in that cell, there's some ion channels, and those ion channels only allow the movement of, say, potassium. Say they're potassium ion channels, and they allow potassium flow back and forth. What if I told you there was 0.2 molar potassium here and 0.02 molar potassium here? What would happen? Okay, the ions flow out until the concentration is the same, right? Why not? Oh, there's a charge imbalance. So I said it's selective for potassium. So if potassium flows out, say there's also, Cl minus over here. The Cl minus can't flow with it. So it's kind of like the same thing here. Like, why didn't every single electron go over? Because you get an electrostatic potential. And that electrostatic potential affects what? Electrochemical potential. And it's the electrochemical potentials that determine the equilibrium. Okay, so do this in your notes. Calculate it right now. Based on the definition of electrochemical potential. What happens at this system at equilibrium? What is phi alpha, phi beta? And we can even be simpler here. Let's say this is C, constant or activity K plus in beta inside the cell. And let's say this is activity K plus outside the cell. Derive an equation that tells me the electrostatic potential across the membrane at equilibrium. Okay, so I think what you're telling me is we need to expand this term into its constituents, right? So what are the constituents of the electrochemical potential? In phase beta of K plus, right? Plus what else? Keep going. RT, Ln, the activity of potassium in beta, plus what? Phi, and why did I drop Z? There was a Z here. Plus 1, right? That's right. Good. And what's on the other side? Well, it's the same stuff, right? It's going to be mu naught K plus alpha plus RT ln A activity alpha K plus F Phi in alpha, and I better put in beta here so we don't get confused. Okay, so which terms, do these terms cancel? Or we have to figure out what they all are? The mu naughts cancel, right? Because does it matter? The standard state chemical potential is going to matter if it's in phase alpha or beta. No, it's defined in a specific standard state. That's just a reference state. So we can get rid of that. Those cancel. And then we can collect terms, right? Yeah, let's do this. So Phi alpha minus Phi beta is going to be equal to RT over F, that term minus that term, ln activity K plus beta over activity K plus alpha. And when we see something like this, RT over F, ln ratio of concentrations, we say that's the Nernstian. It's not the Nernst equation, this is a Nernstian relationship. Here, right, this is actually very similar to this. Somebody tell me how it's related to this? So here I have a membrane that only allows positive charges to exchange, to come to equilibration, to make a potential. to set up an electrostatic potential across the interface. What kind of charges can exchange at this interface? Electrons, negative charges. Can positive charges exchange at this interface? So for a positive charge to move, what would have to happen? You have to have a sodium plus move. This is an interface that is selectively allowing only electrons to move. Right? Electrons can leave behind sodium pluses, but those sodium pluses can't follow the electrons at room temperature. So what happens if I heat this whole system up in vacuum to say 1,000 degrees Celsius? What happens? It will probably melt and become an alloy. That's chemistry, right? This is electron transfer. Chemistry is movement of atoms along with electrons usually. So let's formulate a cell potential. Formulate a cell potential. We consider this reaction zinc plus 2AgCl plus 2 electrons in a copper wire. And that's going to be in equilibrium with zinc 2 plus. It's going to be in an aqueous phase plus silver metal in another silver wire plus 2 Cl minus plus 2 electrons in another copper wire. Notice that one is copper prime, this one is copper. We can write the cell schematic for this in a copper wire. So what things are being oxidized in this equation, red left to right?
Zinc.
Zinc. So copper with a copper alligator clip, for example, clipped onto a zinc wire, right? In equilibrium in solution or in contact with a solution with what net? Zinc 2 plus, Cl minus, which is in contact with my cathode, which has AgCl, in contact with silver, in contact with what? Copper. But I better put a copper prime here. These are different copper wires, right? So at equilibrium, what can I say about the electrochemical potentials of all these species? So in equilibrium, if I take an infinitesimal amount of all these species and make an infinitesimal amount of all these species, what should be the free energy change? 0. So making a teensy tiny bit of this stuff should have the same free energy change as consuming an teensy tiny bit of this stuff. Because delta G for the reaction at equilibrium is 0. Forward rate, backwards rate the same. There's no net driving force at equilibrium. So the electrochemical potential of zinc in zinc plus 2 times the electrochemical potential of AgCl in AgCl plus 2 times the electrochemical potential of the electrons in copper prime, right? That has to equal the electrochemical potential of zinc 2 plus and the electrolyte. Let's see, what do I call that? In the solution. In solution, S is going to be solution, plus 2 times the electrochemical potential of silver in silver, plus 2 mu bar chloride in solution, plus 2 mu bar electrons in copper. So it turns out we can do something here very nice. So we can identify something as the cell potential. So when you use a voltmeter, you measure the voltage of something, what you're actually measuring is the electrochemical potential of the electron on one clip versus the other. Because it's the sort of the driving force for those electrons to move from the red side to the black side, for example, through the voltmeter, which drives a little teeny current, which causes that little needle to deflect a little bit. So it turns out the cell potential is going to be given by this. So 2 mu E copper prime minus mu E copper. So that's the difference in electrochemical potential of the electrons in the 2 copper clips equals negative 2 Fe copper prime minus Fe copper equals negative 2 Fe. So you can kind of see this right away. This is sort of the free energy of the electrons, right? Here. And if I want to convert that to sort of a potential, I need to account for number of electrons, for Faraday's constant, the charge per mole. Because we're going from sort of an energy to a potential. And I can write, what's the mu bar of an electron again? What's that defined as? So it's the chemical potential of the electron minus Fp. Now, why do we have an activity term in here? Because we assume the activity term is negligible because the concentration of the electrons in any given material isn't going to change much, right? Because you can't really change like the concentration of electrons in platinum. Otherwise, you'd be like taking an electron off every platinum and the thing would explode. So the concentration is roughly constant for a given material. Right? You're not going to change it very much. So we ignore that activity term. And so this goes in here, right? And if I plug this in for the two coppers, what happens is this term cancels out. You see that? So I plug this in for this and this. I have the two P's left over, but that term cancels out because they're both copper. Right? This is something specific to copper. So now I actually have a way, I've identified the cell potential as a component of that equation. And what we're going to try to do is we're going to try to use this equation to derive the equilibrium cell potential. So now at least we know what the cell potential looks like, right? It looks like this term. So if I rearrange this, okay, so anyways, 2Fe, so I'm going to identify those terms here, right? I'm going to identify these terms, difference in those terms, and I'm going to collect them, and I'm going to get this, which is our cell potential, equals mu bar zinc 2 plus in solution plus 2 mu bar silver plus 2 mu bar in solution of chloride minus 2 mu bar AgCl minus mu bar zinc in zinc. So I just collected the terms. Now, what is the definition of mu bar of a given species again? Chemical potential at standard state plus RT plus CF. So first of all, are there any terms up here that I can get rid of that may not be important or that are zero, for example? So this one, and this one you think are zero. Why is that? So okay, so definitely what I can do is I can say all the neutrals, right? I can get rid of the bars. I can do that. Okay, so let's expand this and write this out in terms of all the species. We'll write negative 2Fe equals mu naught zinc 2 plus in solution, right? Plus RT ln activity zinc 2 plus in solution. And I got rid of the P's. Oh, no, wait, I need to account for the Phi of zinc 2 plus, right? So I'm expanding this term. So I need to go minus 2Fe of solution, right? So I've just taken this and I've expanded this term. Is this, right? Okay, and then I need to do this term. That one's going to be easy. Plus 2 mu AGS plus. Yeah, we also lost an F. 2Fe. Okay, good. So this term, right? This term's easy because there's no activity component. It's pure, right? And then the next term, I have to write this term, plus 2 mu Cl minus S naught plus RT ln A 2 RT ln A Cl minus in solution minus Fp solution, right? Times 2. Okay, good, let's keep going. This term, what's this term? Minus 2 mu naught AgCl, because it's pure, there's no activity term, right? It's just a pure solid. We define activity of a pure solid as 1. So that's our reference state. So even though, like, you know what, in water, like you write an equilibrium expression, like in general chemistry, and you have water in the equilibrium expression, and water is your solvent, what do you put in for its concentration? 1, because it's the solvent. And what that really means is you're using your reference concentration to calculate an activity, and your reference concentration is 55 molar for water. Your reference concentration for solutes is 1 molar typically, right? So that's why you put concentrations in an equilibrium expression, because you're approximating them as activities. Activities are actually unitless because their concentration is divided by a reference concentration. also times the activity coefficient. Here, what's the last term? Oh, zinc. Minus mu bar zinc and zinc. Okay, so we can cancel some things out here, right? So that nicely cancels out with that. And we can arrange this, right? So we basically have products. This is a product. This is a product. So we can write, let's just write this out over here. I'll be easier to write it again. And so very simply, we're doing all this work to get something very simple. Negative 2Fe equals, well, this is a 2-electron reaction, right? That I just wrote, it was a 2-electron reaction of zinc 2 plus. So that's N, right? So this is NFe, negative NFe. What does negative NFe equal? Delta G. And that's equal to mu naught in solution, zinc 2 plus 2 mu Ag naught in Ag plus 2 mu Cl minus naught in solution. So this is, I'm just taking that from over here, right? That's that, plus that, plus that, and there's going to be some activity terms. Oh, we're going to define this as delta G naught. Put a naught there, saves us. So this is going to be the standard state, right? So at standard state, I don't have to worry about activity terms. They all go to 1. All the activities go to 1, right? So the activity terms go away. Natural log of 1 goes to 0. And so I can write the standard state, delta G naught, from that equation by setting the activity terms to 0 equals minus 2 mu naught AgCl, and minus the last term, which is mu naught zinc and zinc. Okay, so this is like you could have done this on your own, right? Like delta G equals products minus reactants. So these are sort of like molar free energies, which you could look up in a table. It's mu naughts. So these are all, it's all connected, right? So we said, okay, well, let's consider the special situation where all the activities are unity. And we're going to define that. So let's write that more specifically in your notes. Define when A equals 1, standard state. AI equals 1. And that's going to give us these knots. And that's how we can get this expression. So then we can go back here and we can say, okay, I want to calculate for not standard state, right? By the way, at the end, what should we get? If we're calculating the self-potential? The Nernst equation. Exactly. Good job. So we can rewrite this equation below as negative 2Fe equals this term, right? I'm collecting all these terms from this equation. Negative 2F mu naught plus RT ln A zinc 2 plus S plus 2RT ln A Cl S solution. And how do we write this in any way? Get that, put that 2 in the logarithm. If I want to put the 2 in here, what do I need to do? I raise it to the second power, right? So I take this and I raise the term in the log to the whatever power that the prefactor is. So I can do that, and I can rewrite this in a form E. So I'm going to divide by negative 2F, and I'm combining the logarithms. E equals E naught minus RT over 2F ln. Let's see here. A S zinc 2 plus times A Cl minus S squared. Okay. Which is actually the Nernst equation for the cell. Right? Concentrations of products over concentrations of products to their stoichiometric coefficients. So if you look at the cell equation, which I've now erased, of course, but if you look back in your notes, products raised to the power and the stoichiometric coefficient divided by reactants, and the reactants are all terms at standard state, which fall into E naught here. Right? Silver chloride, silver, those chemical potentials, zinc, those all fall into the standard state term, which we defined over here. So this is just a Nernst equation. E equals E naught minus RT over NF ln Q, where Q is the reaction quotient written in terms of activities. So I already said this, but the Fermi level, so I'm going to give one quick example and then we'll be done. So imagine I have a solution. You actually guys did this in lab, I think. You take like a platinum wire or a metal electrode, and I have some iron 2+ and some iron 3+ in solution. And then you measure this potential versus the reference point. And I say, well, what determines the potential I'm measuring? How would you figure that out? Nernst equation, right? So it would be E, versus AgCl equals E naught versus AgCl plus RT over just F is the one electron, Fe activity Fe3+ over activity Fe2+. Sorry, change the sign and put the O and R. Okay, so you could do that. That's what you do. We could get that equivalently, and this is kind of the neat part here. So I can write an equation: electron in the platinum, right? That's where electrons come from, plus an Fe3+ goes to an Fe2+. So let's use the electrochemical potential. Mu bar of an electron in platinum plus mu bar Fe3+ equals mu bar Fe2+ and mu bar electron platinum then equals mu bar Fe2+ minus mu bar Fe3+. And that's what you measure. You actually measure this, and then if you go and write the definition out of these terms, right, of all these terms, you actually get the Nernst equation. Because the activity terms will show up over here. The other terms will show up here. This is just a half reaction, right? So then, of course, they're all referenced, bringing the reference potential. So this is kind of interesting, like electrochemical potential of the electrons, the Fermi level, the position of the electrons in the metal is the difference between the chemical potentials of the two species that are in electrolyte, because everything is in equilibrium, right? So I'm taking an electron and iron 3+ and make one iron 2+, I'm not changing the energy of the system. Delta G for this reaction is 0 in equilibrium. We're done. Sorry for going a little late. Thank you for your attention, and I'm happy to take any questions on your way out.